several sequences of the data. This isn't every pass. It covers, if I used every one, it would be line after line after line as it marches through the northeast. So what's interesting here is if you look at the model runs at this time, and this correlates to this time here, you see everything going to the northwest correlates pretty well to the model. Over here to the northwest correlates fairly well over in here. And then to the northwest correlates fairly well over in here. But the satellite does not detect anything down here. And yet the model shows something down there. And this was an interesting lesson to us because before this event, we used to tune the models to match the satellite data. That was our ground truth. And we had this event occur, and here's what we saw. This is the animation on the model running. These stars excuse me, are aircraft in a region. The stars turn red when they report in what they saw regarding the eruption. So let's see if this runs right. This plane was taken off from San Francisco, and he reports in smelling sulfur in the atmosphere. That report comes in right at the time the model got to him. You see the star turn red? That was one of the first times we ever had an airborne observation like that that had some kind of confirmation of what our models were predicting. So that was pretty exciting. It tended to show us something was involved that we could actually quantify in this data. And it also taught us never to try tuning our models to the satellite data because it's not always necessarily right, and that there are limitations to the satellite data. Now, to back away from this and say, okay, what have we done? What have we done to make this work as smoothly as possible? Well, what we've done is we also have developed a bunch of web tools. And these web tools are to facilitate volcano eruption cloud monitoring and analysis. But I should point out, not only does this apply to volcanoes, but it could apply to SO2 from factories and things. You could apply it to a lot of other activities. So I put some stars by things that are probably be most interesting. This is an observational database we use for monitoring. We have something down here called the Image Flipper. This is a weekly report. This is, this sounds silly, but once you get too high up in the administration of the university, or you've been there too long, you get involved in a lot more management reports to come out and everything else to do. Anything you can to make it simplified. Well, creating a database and automated that weekly reporting, so we're all free of that in Python. And we used to spend a good week every month working on reports. Bi-monthly reports, and then hotspot view. And I'll show you a couple examples of what these look like. These are web-based tools. This is the database system. Somebody monitors the volcanoes every morning, every afternoon. They enter information to the database regarding that if they spot anything. So if they spot a plume, let's say, they're going to give, I can't read that from here, they're going to give the length in 73 kilometers, in this case, the height 8 kilometers, and the direction 115 degrees, and the value is temperature value minus 55. Every eruption, every plume, everything observed that has some type of information entered into this moment. Yellow means it's on alert, that we're focusing energies on it, and green means that it's quiescent and nothing going on. Now we have this other category called, I forget what it's called, unknown or unresolved. That's where we don't have seismic instruments on the volcano to tell what it's doing. Also, we do this system manually. The system automatically scans looking for thermal anomalies or scans looking for ash clouds. When it sees something, it will send us a telephone message to our cell phones alerting us, and we can log in right from our cell phones. It will send if we have it turned on our computer voice will talk and alert us to take a look at some data coming in. It sends an automatic email messages. So whether we're at home, on travel, or whatever, if we have these systems turned on, we're hooked into the network. For the last few years, I've turned it all off. I've let everybody else know. I got tired of getting all these messages. And this is what the Image Flipper looks like. Image Flipper is kind of cool. We've got 2 minutes left, I think. Okay. Image Flipper is kind of cool. Every pass that comes in, is automatically processed to look at on the flipper. So that means you can set the flipper to tell you, okay, I want to see the images for the past 24 hours, for the past 12 hours, and then that imagery will flip through those images in time sequence over that period of time. And you can define what bands you want to look at and look through the flip. Now, if you're looking for activity, this is a really fast way. Just sit there and watch the computer, and it'll pick up anything that's new that's going on, and you can freeze it right there. And so that's the basis to a lot of our upgrades and reporting. We can also put this in Google Earth, which is important because then we get the geometry right. This is the hotspot viewer. Again, this is a 40 by 40 kilometer size area to look at specific hotspots. This goes into Google Earth as well, which again gives us geometry. You know, if the hotspot is on the slope of the volcano, then we know there's a good chance we have a lava flow or a hot debris flow or something else. If it's right at the summit, we're probably looking at the vent or a dome. And then based on these web tools and the observation database, we have almost 20 years of detailed data that we've managed to enter into the system. We can look at profiles. This is the time temperature profile over, let's say, a week of the hotspots at, I think it's Klishevskoye, yes, volcano. And this, you can see the things saturating for the system. Down, this is the band 4, this is the split window data. I think that's what I'm saying that right. I can't read, yes, the blue one and the split window, these would be the ash clouds coming up. So we've got this marvelous database of tens of images daily or more, all processed and analyzed in the system. I'm going to skip this because I'm running out of time. This is actually a time sequential composite of the eruption of Cleveland volcano, which was really interesting because I'll talk about this tomorrow, but this defines the area that's impacted. And then my last 2 slides just talks about how fast does it take to do all of this. Well, it's about 10 minutes, maybe 15 minutes for us to get through the system, for the data we receive, get through the system, and a report going out by an analyst, an alerting system. And this is the communication flow, going from the initial analyst on down through reviews and the review process until it pops out the other side as critical information sent to the FAA, the National Weather Service, the Volcanic Ash Advisory Center. So, that's it in 1 minute over or so, sorry. I think it's interesting here, I just want to point out, one thing that was really fascinating to me is having this real-time feed coming into our network. There's all kinds of information you can suck out of the data and enter into a database that if you took a grad student and said, okay, I want you to analyze the last 10 years of thermal anomalies at Klishevskoye volcano. With all the data we have, that would be a totally mindless job. I guess it'd be good for grad students to do, but it's not something you necessarily want them to do, or he may not want, or she may not want to do it. So this is really a clever way, it's a cool way to do data extraction. And so I think I'll leave it at that. Thank you very much.